Alright, we have a pretty interesting problem in this one. So in this scenario, we are treating a gas using an absorption column. And the solvent we're using to absorb the impurity is being regenerated in a stripping column. So we take the treated gas, and some of it is diverted to the stripping column, and this is in fact what will be used to regenerate the solvent. And we're tasked with finding the number of stages in the absorption column, the inlet liquid concentration for the stripping column, the outlet gas concentration for the stripping column, and figuring out how much of the gas is sent to the stripping column. So let's get started by just writing down what we know. So let's start with the absorber. And so we know that the equilibrium relationship is y equals 0.5x. And we also know that since the inlet gas concentration is 15% of our impurity, this means that this is a concentrated system, so we have to use mole ratios instead of mole fractions. So the liquid flow rate is 800 moles per day, and the gas flow rate is 1400 moles per day. The next thing to do is to just write out the known concentrations. So let's start with x0, which we know is equal to 0.5%. Next we have y1, which is also 0.5%. yn plus 1 is equal to 15%. And then we don't know xn. So first of all, let's convert all of this to mole ratios. So the formula for mole ratios is simply x divided by 1 minus x. So let's do that. Now, in order to find the outlet concentration of the liquid, we'll need to perform a mass balance. We know that the amount of impurity that's transferred is equal to 14.5% of the gas flow rate, the total gas flow rate. So let's write that down. Which is 203 moles per day. So we know that the final mole ratio of xn is going to be equal to the total transfer flow rate plus the existing amount of impurity divided by the inert fluid rate. So this is going to be equal to 203 plus 4, and all that divided by 796, which gives us a mole ratio of 0.26. Now we can find the corresponding mole fraction by simply taking this value and dividing by 1 plus the same value, which is about 20.6%. We now have everything we need in order to trace an operating line and an equilibrium line. So let's start by just writing this out. So we have our liquid mole fraction and our gas mole fraction, and when we're tracing this, we're going to choose some arbitrary values. So let's choose 0.02, and let's just have increments of 0.02 until we reach 0.20, which is going to be our final concentration here. Now the equilibrium relationship is going to be equal to 0.5 times x. Now the next step is to convert all this into mole ratios. So let's take capital X and capital Y, and once again, to convert mole fractions to mole ratios, it's simply the mole fraction divided by 1 minus the mole fraction. Now let's go ahead and plot that. Okay, so this is our equilibrium line. We can see that because we're using mole ratios, it is slightly curved. So now let's go ahead and trace our operating line. Now, for a operating line with mole ratios, the equation is almost identical to the normal operating line equation, except that we need to use mole ratios and we need to use the inert flow rates instead of the total flow rates. So okay, so now that we have our operating line, let's go ahead and trace it. And as we can see, this operating line is above the equilibrium line, which is what we would expect from an absorption problem, and so we're good to go. Now then, the only thing left is to do a McGill analysis, and then we can find a number of stages. I'm going to bring this graph into another sheet so we can make it bigger. Alright, and now let's just step down the column until we find a number of stages. Okay, so now that we step down the column, the number of stages is the number of times we contact the equilibrium line. So we have 1, 2, 3, 4, 5, 6, 7, 8, 8 stages. So we can go ahead and write and enter that here. Okay, now for part 2 of this problem, we have an already existing column with 4 stages, and so now we need to find the gas flow rate and the outlet gas concentration. So once again, let's go ahead and write what we know. So the stripper has an equilibrium relationship of y equals 3.0 times x, and so the inert liquid flow rate is still equal to 796 moles per day because this is a closed loop, and the gas flow rate we do not know. So in terms of the concentrations, we do know that the outlet liquid concentration needs to be 0.5% mole fraction, and the inlet gas concentration needs to be 0.5% mole fraction. So xn is equal we also know that the inlet liquid concentration needs to be the same as the outlet liquid concentration of the absorber. So x0 is going to be equal to 20.6%. Finally, we don't know the outlet gas concentration, so that is something we're going to have to figure out. Okay, so based on what we know, we should first trace the equilibrium line. So let's write x, y, capital X, and capital Y. And let's start with 0, and let's do an increment of 0.005. This will make things easier down the road, as we'll see. And let's do this increment until we reach the final exit concentration, which is 20.6%. Now we'll just calculate the equilibrium using the equilibrium relationship. And finally, let's calculate the mole ratios. Now let's trace our equilibrium graph. Okay, now we have our equilibrium graph. And before I proceed, I want to say that this actually would be a perfect problem to use the Kremser equation if it weren't for the fact that the streams are concentrated, because this allows you to simply solve for the variable that you want. In this case, the flow rate. But now, since this is a concentrated system, we're going to have to use McGill analysis, and since the number of stages is known, we will have to use a trial and error approach. So to do that, let's first take into account the operating line equation. While we don't know the flow rate, we're going to have to guess different values of the flow rate, and until we find one that gives us exactly 4 stages. The final exit concentration will be given by where the operating line passes through once we have the correct flow rate. So we're going to first take the operating line equation and simply use the inner gas flow rate, and then we're going to iterate until we find something that works with 4 stages. And this will just have to be done manually because we have to trace the McGill relationship by hand. You'll notice that in this particular equation, I'm using xn and yn plus 1 instead of x0 and y1. And this is simply because we have these values, and so we can use them directly instead of having to calculate something for y1. Okay, so now that we have our operating line equation, it's not working right now because there's no value here. We can simply go ahead and trace it. And then we can adjust the flow rate as needed. So let's say we pick 500. You can see that this changes the slope of the operating line. And so we need to adjust this until we find one that gives us a slope of, well, that gives us 4 stages. So let's start with 1000 as an arbitrary value. So the way I've set up the graph makes it quite easy to trace the McGill lines because the McGill lines will start at the end of our operating line, and they will continue to the very first dot here, or the second dot actually. So I'm going to make this marker a little smaller to make drawing it a bit easier. And now let's zoom in and take a look. We're going to trace our first equilibrium relationship, starting from the first point. So you can see that after we trace this, we only have 3 stages, and we're way above the operating line. So this means that 1000 is too high of a flow rate. So let's go ahead and delete these lines and choose a lower flow rate. So let's pick 500. Now the slope is a bit tighter, so this should give us a better result. Okay, so now we've drawn the McGill daily lines with 500 moles per day, and we can see that with 4 equilibrium lines we don't get to the end yet, so that means that 500 is too low. So let's choose another value. Let's choose 750, so a value in between both of these, and let's see what we get. Okay, so now we've traced another 4 equilibrium stages. With this flow rate, you can see that we're above the operating line after 4 stages, so we need to go a bit lower. So let's pick 700. Okay, so after doing that, you can see that we barely make it under the end of the line, so we just need to increase this a tiny bit more, and we should be right on the dot. So let's pick 725. After tracing the McGill daily line for 725 moles per day, it looks like this is roughly 4 equilibrium stages. So we can say that the final value is 725 moles per day, and y1 is going to be equal to the end of this operating line, which is 0.285. And that is our solution.